math learners. Our lesson for today is about tautologies, contradiction, and fallacies. Let us have first tautology. Tautology is a compound statement which is true for every value of the individual statements. It doesn't matter what the individual part consists of, the result in tautology is always true. The word tautology is derived from Greek words where tauto means same and logi means logic. Let us have an example. You are going to determine whether the proposition is a tautology. Given the negation of H implies H. So let us construct now the truth table of this given proposition. First, we have H here, then the negation of H, and then we have now the negation of H implies H. So if H is true and negation H or not H is false, then the result is true. If H is false and not H is true, then not H implies H is false. So the truth value of not H implies H is TF, or true and false. Therefore, the proposition of not H implies H is not a tautology. All the results here must be true in order to consider the given proposition as tautology. Next example. Still, we are going to determine whether the given proposition is a tautology. Given M or not M. So let us have M here, then not M, then M or not M. So if M is true and not M is false, since this is OR, then the result is true. And then if M is false and not M is true, the result is also true. So we have T here and T. So both are true. So the truth value of M or not M is T and T. Therefore, the proposition M or not M is a tautology. Next example. Given P implies the disjunction P or Q. So let us have P here. Then for the Q proposition, then we have P or Q. And then lastly, we have the given P implies the disjunction P or Q. So if P is T and Q is also T, then the result of P or Q is T. And the implication of P and P or Q is true. If P is T and Q is F, then the disjunction of P and Q is T. And then the implication is T. If P is false and Q is true, then the disjunction is true. And for the implication, it is also true. And if P is false and Q is false, the disjunction is false. And the implication is true. Since the truth value of the implication is true for all values of the individual statements here, all true, Therefore, we consider the implication as a tautology. So to identify the proposition whether it is a tautology, all the values of the individual statements should be all true. Next, let us have now the contradiction. The contradiction is just the opposite of tautology. When a compound statement formed by two simple given statements and performing some logical operations on them gives the false value only, then it is called a contradiction. For example, so you determine whether the proposition is a contradiction. Given n and not n. So for the truth value, we have first n here, not n, then the conjunction of n and not n. So if n is true and not n is false, automatically the result is false. And if n is false, not n, if this is false, so not n is true, then the conjunction is also false. Then the results are all false. Then the truth value of this conjunction is f and f. Therefore, the proposition of the given conjunction is a contradiction. Another example, the negation of the implication x and y, or x implies y, or the implication of y and x, or y implies x. So let us have first, the first column would be the truth values of x. Second column, the truth values of y. Then third, the truth values of x implies y. Fourth column would be the truth values of y implies x. Then the fifth column would be the disjunction of the two implications. And then for the last column, we have the negation of the disjunction of the two implications. So if x is true and y is true, the implication of x and y, or x implies y, is also true. And then for y implies x, it is also true. So the disjunction of these two implications is also true. And the negation of this disjunction is false. Next, if x is true and y is false, then the implication of x and y, or x implies y, is false. And for y implies x, it is true. And for the disjunction, we have true. Since this is true, the negation of this is false. Next, if x is false and y is true, f implies t is true. And y implies x is false. And the disjunction of these two implications is true. Therefore, the negation of this is false. If x is false and y is false, then x implies y is true. And y implies x is also true. So the disjunction of the two implications would be true. And since this is true, the negation of this is false. So the results of the last column we have all false. The truth value of the negation of x implies y or y implies x is false for all the values of the individual statements. Therefore, the proposition is a contradiction. Again, you will consider the given proposition as a contradiction if all the resulting values here are false. Next, let us have fallacy. Fallacy is an incorrect argument in logic, which is a result of invalid reasoning. An argument is an assertion that a given set of statements called premises results in another statement called conclusion. An argument is valid if the premises are true, and the conclusion must also be true. Some fallacies are popular beliefs. Some are often persuasive. Some are unintentionally created, and some are intentionally created for deception. Fallacies are either formal or informal. Let us have first the formal fallacy. Formal fallacies, or can be called as deductive fallacies or logical fallacies, are invalid arguments due to a flaw in logical structure. A formal fallacy, however, may have a true premise but a false conclusion. Here are some common formal fallacies that are often used unintentionally or otherwise. Affirming the consequent, undistributed middle, denying the antecedent, affirming a disjunct, and denying a conjunct. Take note, you have to research the other types of formal fallacies which are not discussed here. Let us have examples of formal fallacy. First, for affirming the consequent. Affirming the consequent, sometimes called converse error, fallacy of the converse, or confusion of necessity and sufficiency, is a formal fallacy of taking a true conditional statement. So let us have the first premise. Humans are mammals. The second premise, jaguar is a mammal. For the conclusion, therefore, jaguar is a human. The truth of the conclusion is independent of the truth of its premise, since jaguar might be a mammal without being human. He might be a lion. Another example. The first premise is all Filipinos are hospitable. John is hospitable. And the conclusion, therefore, John is a Filipino. Here, John may be hospitable but not a Filipino. Therefore, the conclusion may be false. Next, for undistributed middle. The fallacy of undistributed middle is a fallacy that is committed when the middle term is a categorical syllogism is not distributed. It is a logistic fallacy. For example, the first premise is all triangles are polygons. The second premise is all quadrilaterals are polygons. For the conclusion, therefore, all triangles are quadrilaterals. The conclusion is false since triangles are not quadrilaterals and the middle term polygons is not distributed as a subject and as a predicate. Another example. First premise, every integer is a rational number. Second, some decimals are rational numbers. And for the conclusion, therefore, some decimals are integers. So the conclusion is false since decimals are not integers. Next, let us have denying the antecedent. Denying the antecedent, sometimes also called inverse error or fallacy of the inverse. It is a formal fallacy of inferring the inverse from the original statement. For example, the first premise is, if you are a ski instructor, then you have a job. Second premise, you are not a ski instructor. Therefore, for the conclusion, you have no job. So the premises may be true, but the conclusion does not follow from the premises because it is false. He may not be a ski instructor, but still he has a job. Another example, if Law is an Alphonsian, then he knows that the official publication of Sachs is the Beacon. Second premise, Law is not an Alphonsian. And the conclusion, therefore, he does not know that the official publication of Sachs is the Beacon. Law may not be an Alphonsian, but still he knows that Beacon is the official publication of Sachs. The conclusion may be false. Next, let us have affirming a disjunct. The fallacy lies in concluding that one disjunct must be false because the other disjunct is true. In fact, they may be both be true because or is defined inclusively rather than exclusively. For example, the first premise is Max is a mammal or Max is a cat. Then, second premise, Max is a mammal. Conclusion would be, therefore, Max is not a cat. So the inference is unsound because all cats by definition are mammals. Next example, I really love chocolate, or I seriously lack willpower. Second premise, I know I really love chocolate. Therefore, I cannot lack willpower. Ignoring the possible false dilemma, the fact that one really loves chocolate does not automatically exclude the other possibility of lacking willpower. Next, let us have denying a conjunct. A formal fallacy in which the first premise states that at least one of the two conjuncts, the antecedent and consequent, is false, and concludes that the other conjunct must be true. For example, first premise is I am not both a moron and an idiot. Second premise, I am not a moron. The conclusion, therefore, I am an idiot. I might be an idiot, but the truth of both premises does not guarantee that I am. Therefore, this argument is invalid. Being not both a moron and idiot only means that if I am not only of the two, I am simply not one of the two. We cannot logically conclude that I am the other. Another example, I am not both a Christian and a pagan. I am not a pagan. Therefore, I am a Christian. The truth of both premises does not guarantee that I am a Christian. Therefore, this argument is invalid. The form of this formal argument is invalid. Being not both a pagan and a Christian only means that if I am not one of the two, I am simply not one of the two. We cannot logically conclude that I am the other. Let us have now the informal fallacy. So let us have the definition. Informal fallacies are arguments whose premises adequately support the validity of its conclusion. In many cases, informal fallacies are defective both in content and structure. Informal fallacies are a type of incorrect argument in natural language. Fallacies, despite being incorrect, usually appear to be correct and thereby can seduce people into accepting and using them. Here are some common informal fallacies. One, we have the fallacy of ambiguity or equivocation. Fallacy of appeal, we are using the appeal to authority. And fallacy of composition. So you are again encouraged to research on the other types of informal fallacies which are not discussed here. Let us have the fallacy of ambiguity or equivocation. The source of the error for fallacies of ambiguity or fallacy of equivocation lies in the usage of language. The term or the phrase in an argument has occurred at least twice and is exploited or deliberately misused. This is due to the fact that many terms in natural language have ambiguous or vague meanings. Ambiguous terms have several meanings, while vague terms have an unclear meaning. Let us have an example. The first premise is feathers are light. Second premise, what is light cannot be dark. And the conclusion, therefore, feathers cannot be dark. So the source of this fallacy is due to the ambiguity in the term light, which is used first in the sense not heavy, and the latter in the sense bright. Another example, the end of life is death. Happiness is the end of life, and the conclusion, therefore, death is happiness. The two premises have different meaning. The problem arises when the term happiness and the phrase end of life are misused. The conclusion also has another meaning. Let us have the fallacy of appeal. And we are using the appeal to authority. These fallacies attempt to persuade people with irrelevant information, appealing to emotions rather than logic. The appeal to authority uses the opinion of an authority or famous person to support an assertion. This line of argument is not always incorrect. For most things in our lives, we have to rely on the other word of an authority. For example, Joe said that 2 plus 2 equals 4. Second premise, he has an advanced degree in mathematics. Therefore, 2 plus 2 equals 4. The fallacy lies in attaching the second premise, which is not relevant, and used opinion of authority in order to give credence to their argument. Another example. The first premise is a commercial claims that a specific brand of cereal is the best way to start the day. The second premise is Michael Jordan says that it is what he eats every day for breakfast. Therefore, that specific brand of cereal is the best way to start the day. They are claiming that it must be true because it is eaten by Michael Jordan, who's said to be an authority on the subject. Whether the person is actually an authority or not, the logic is unsound. Instead of presenting actual evidence, the argument just relies on credibility of the authority. Next, let us have the fallacy of composition. This fallacy occurs when we assume that if all the parts have a given quality, then the whole of the parts will have it as well. It is committed when the characteristics of some are transferred to another. We jump to a conclusion without concrete evidence. For example, the first premise is if all of the basketball team's players are fast runners, high jumpers, and winners, then the team is a winner. Let us have the second premise. All the basketball team's players are fast runners, high jumpers, and winners. Therefore, the team is a winner. The problem here is that the individuals must work together to make the team a winner. Another example, every member of the gymnastic team is an outstanding dance sports performer. The gymnastic team is an outstanding team. Let us have the second premise. Every member of the gymnastic team is an outstanding performer. Therefore, the team is outstanding. The problem here is that every member must work together to make the team an outstanding. It is not necessary that every member of the gymnastic team is an outstanding performer. All they have to do is to have a teamwork. Next, let us have the fallacy proofs. In world of mathematics, countless brilliant minds dedicate their lives in an effort to prove that seemingly impossible. Interestingly enough, through the plethora of established proofs which has tremendously impacted the scientific world, a few false proofs have also survived the scrutiny of mathematicians. However, rather than simply dismissing such fallacy proofs as unfortunate mistakes, equally valuable lessons can be learned through the understanding of why such fallacy proofs were able to take on the facade of a real proof. Let us have an example. Supposing we are asked to prove that 1 is equal to 2. So let us have the proof in this manner. Supposing we are going to let A is equal to B, and then we have to multiply A to both sides. So A times A is A squared, A times B is AB. And then we have to apply the addition property of equality, wherein you may add A squared to both sides. So add A squared, you also add A squared here. Then you have to add similar terms. A squared plus A squared is 2A squared. Then apply subtraction property of equality. You may subtract 2AB from both sides. So minus 2AB minus 2AB. And then we combine similar terms. AB minus 2AB is negative AB. And then we have to use common monomial factoring. So you factor these two terms, factor out 2, then we have 2 times the quantity A squared minus AB is equal to A squared minus AB into 1 times the quantity A squared minus AB. Then we have to divide both sides by A squared minus AB. Here, the left side over A squared minus AB, right side over A squared minus AB. Then by this time, we can cancel. Can also cancel. Then what is left is 2 is equal to 1. Then we may just apply symmetric property of equality, so we can have 1 is equal to 2. So by this time, we're able to prove that 1 is equal to 2. But this is impossible because 1 equals 2 is false because 1 is not equal to 2. So this is an example of a false proof or fallacy proof. Another example. Prove that 1 is equal to 0. So let us have the proof in this manner. We can expand the square of n plus 1. So the square of n plus 1 is equal to n squared plus 2n plus 1. And then you may subtract 2n plus 1 from both sides. So minus 2n plus 1 minus 2n plus 1. And then 2n plus 1 minus the quantity of 2n plus 1 is equal to 0. So what is left is only the n squared, and then we may subtract again n times the quantity 2n plus 1 from both sides. So minus n times the quantity 2n plus 1 minus n times the quantity 2n plus 1. So you can apply factoring by grouping in this part. 2 plus n and 2 plus n is common. So you write there 2n plus 1. Then negative, you can have n, and the numerical coefficient here is 1. So you can have n plus 1. When you multiply, negative times n is negative n, and negative times positive 1 is negative 1. And then afterwards, you can add the quantity 2n plus 1 squared over 4 to both sides. So this part here, you add. And then you will have to factor the perfect square trinomial. This is now a perfect square trinomial. You can factor this into the square of n plus 1 is n plus 1. And you also have here n plus 1. And then the square of 2 n plus 1 over 4. Factor it. You have 2n plus 1 over 2. Then you have here 2n plus 1 over 2. The middle term is the result when you multiply the first term with the second term of the other, and the second term with the first term of the second, and also the other one. Factor n squared, you have here n and n. Factor this 2n plus 1, the quantity squared, over 4. Then you will have 2n plus 1 over 2. Write it here. And then the middle term again is the result when you multiply n with this and this one with this. Then take the square roots of both sides. So you extract the square root of this and also the square root of this. So the result now is you have n plus 1 minus the quantity 2n plus 1 over 2 is equal to n minus the quantity 2n plus 1 over 2. And then you add 2n plus 1 all over 2 to both sides. So here you add 2n plus 1 over 2, the quantity 2n plus 1 over 2. So you can eliminate this. This is equivalent to 0. And also this one. This is equivalent to 0. So what is left is the n plus 1 equals n. So only n here. So what you have now is to subtract n from both sides. So n plus 1 minus n, then n here minus n. So n minus n is 0, n minus n is 0. So we have now 1 is equal to 0. So again, this is impossible because 1 is not equal to 0. 1 is equal to 0 is false. This is another example of a fallacy proof. Do you have questions? If there's none, See you next time. Bye.